The name of the chapter is Current Electricity. We will have to study detailed about current electricity, but we should know why this chapter has been created, current electricity. In this scenario, you will know that when the charges are in two stages, the first one is at stationary and the second one is at motion. When the charge is in stationary position, then you will give its a term electrostatics, but when the charge is in motion, then it will be termed as current electricity. You should remember that electric charges are of two types. The first one is positive charge and another one is negative charge. These two types of charges were termed by Benjamin Franklin. Now we can define here the current electricity that when the charges are in motion, then it is termed as current electricity or electrodynamics. Let's start with the topic electric current. It is also termed as current strength. So we can define it that current strength in a conductor is defined as the rate of flow of charge across any cross section of the conductor. Again, I am repeating that it is the rate of flow of electric charge. I think you should know the electric charges are of two types, the positive charge or negative charge. So you can take any of the charge to define the electric current. Flow of electric charge is measured in ampere, or in another word we can say that the SI unit of electric current is ampere. The electric current is represented by capital I, and we can establish a mathematical relation between electric current and electric charge that I equals Q upon T, or we can say that Q equals NE. So we can establish a new relation that I equals NE upon T. For non-uniform flow of electric charge, we can establish an integral relation between electric current and electric charge as I equals integral of dq upon dt. The electric current flows in a conductor because the conductor have some free electrons. If a substance have free electrons, then there will be a conduction of electric current through that. If electric current is flowing, it means free electrons are present. For the conduction of electric current through a conductor, it is very essential that we will require a alternate source of battery or an EMF. The given figure have two parts. In the first part, the free electrons is not connected with external source of battery. Hence, there is a random motion of the electrons in the given conductor. But if the source of battery is connected with the conductor, then the second figure follows. Means all the free electrons are arranged and they are tends to move in a single direction. The next figure shows that if the number of free electrons are increased, then the magnitude of electric current is also increased, because the magnitude of electric currents directly depend on the electric charges. As you have already studied about Ohm's law for conductors in your previous classes, but once again we are going to define and once again we are going to study about Ohm's law. As we have studied earlier that at constant temperature, current flowing through a conductor of uniform area of cross section is proportional to the difference of potential across its terminals. That means if electric potential is increased, then electric current will also be increased in the similar way. It is the mathematical relation of Ohm's law which shows that the potential is directly proportional to the current and a new term is generated which is resistance. So the resistance of a conductor is defined as the ratio between the potential differences between the two ends of a conductor to the current flowing through it. And the SI unit of resistance is ohm. The resistance is denoted by capital R or small r everywhere. The direction of electric current is opposite to the direction of flow of electron. If external potential is applied, then electrons means free electrons start moving, but in the opposite direction of that free electrons, the electric current's direction is taken off. Now, types of electric currents. According to its magnitude and direction of electric current is of two types. The first one is direct current and the second one is alternating current. Now, if you are going to talk about this direct current, its magnitude and direction do not change with time. Its magnitude and direction do not change with time. Just for an example, A ceiling, battery or DC dynamo are the sources of direct current. In the similar way, alternating current is an electric current whose magnitude changes continuously and changes its direction periodically is called alternating current. AC dynamo is the source of alternating current. In this figure, clearly you are able to see that in the two graphs there are two different currents. The alternating current are shown by the option A and the direct current is shown by option B. Means periodically in the alternating current the magnitude and direction is changing, while in direct current the magnitude of current remains constant. So the first topic of this session is Gauss theorem. It is also known by Gauss law. According to the Gauss law, the electric flux out of a closed surface is equal to the total charge enclosed divided by the permittivity. I think it is a very complicated definition to you, but if you are well introduced with electric flux and permittivity, then this definition will be very clear to you. So let's start from the basic point that electric flux may be defined as the total number of electric field lines passing through a closed loop or surface. It is denoted by phi E is equal to integral vector E dot vector A, where vector E is the electric field and vector A is area of that closed loop or surface. The next equation derives the formula for Gauss law or Gauss theorem, where phi E is equal to integral of vector E dot vector dA, and this electric flux is equal to the Q upon epsilon naught, means 1 upon epsilon naught times the total number of charge enclosed by that surface. Hence you can say that the electric flux depends on three factors. The first one is electric field, the second one is area of that surface, and the third one is the orientation, means the angle between electric field and the area of that closed surface. So you can have one more definition of Gauss law. According to the Gauss law, the total flux linked with a closed surface is 1 upon epsilon naught times the charge enclosed by the closed surface. Mathematically, you can say that the total integral of electric field multiplied by the surface area is equal to Q upon epsilon naught. One thing which will be very adventurous to you that this Gauss law is also in magnetism, means you will have to study this Gauss law in two different chapters. The first one will be electrostatics and the second one will be magnetism. Now we are going to have some applications of Gauss theorem. The first topic will be electric field due to an infinite wire. In this case, first of all, we will define a Gaussian surface. A Gaussian surface is nothing but an imaginary surface which encloses the charge fully, such that the electric flux is perpendicular to each point and the electric potential at every point is equal. There are some essential properties of Gaussian surface. The first point is that it should be closed surface so that a clear distinction can be made between points that are inside the surface, on the surface and outside the surface. The second point is that this surface must pass through the point where electric field is to be calculated. The Gaussian surface may be of any shape or size. There is no fixed shape of Gaussian surface. It varies with your question. Now coming back to our topic, which was electric field of an infinite wire of Gaussian theorem. Consider an infinitely long wire with linear charge density lambda and length capital L. To calculate electric field, we assume a cylindrical Gaussian surface. See, in the previous time we have revised that Gaussian surface may be of any shape or size. In the given figure, you can say that the surface area of the curved cylinder surface will be 2 pi RL. Since it is a cylinder and you have to take the curved surface area, the electric flux through the curved surface will be E into 2 pi RL, which will be the formula of vector E dot vector A for that cylindrical Gaussian surface. And according to the Gauss law, you can say that phi equals Q upon epsilon naught. Putting the value of phi over here, it will be E into 2 pi RL equals lambda L upon epsilon naught. See, area has been kept here as 2 pi RL and the Q has been interchanged by lambda into L from linear charge density. See, L and L will be balanced from the left hand side and right hand side, and by sending this 2 pi R to the right hand side, you will have E equals lambda upon 2 pi epsilon naught into R. Our next application of Gaussian theorem is that electric field due to an infinite plane sheet. In this case, we imagine an infinite plane sheet with surface charge density sigma and cross-sectional area capital A. The position of the infinite plane sheet is given in the figure below. In this figure, you will come to see that the electric fields are being generated toward the both side, means left side and right side. So if you are going to calculate the total electric field, then it will be the algebraic sum. But you will see one thing more, that these electric fields are in opposite direction. Hence, we can write phi equals EA minus, again in bracket, minus EA, which will be equivalent to phi equals 2EA, because minus into minus it will be converted into the positive sign. Then we can write 2EA equals sigma A upon epsilon naught. This sigma A has came from the formula Q upon epsilon naught, where Q has been changed here as sigma into A. This A and A will be balanced from both sides, and by transforming this 2 to the right hand side, it will be equivalent to E equals sigma upon 2 epsilon naught, which will be your last formula. In the same way, you can find out the electric field due to a uniformly charged thin spherical shell, as it is very simple and it is based on the previous derivations that we have done earlier.